So our last speaker of this session will be Joseph Casamento from Cornell.
I can put this. Is this mic okay? All right, afternoon everyone. My name is Joe. I'm a fourth year graduate student at MSc at Cornell, and here to hopefully get you further excited about hexagonal oxides. And today we're going to talk about lutetium iron oxide 113 and what we've been doing to try to integrate it with the Nitride optoelectronics platform. So again, just a brief overview. One of the things, obviously, the community we're still after in a large context is looking for magnetoelectric multiferroics. So we want to be right at the center of this, Venn diagram here, where we want controlled coupling between magnetization and electrical polarization, ideally ferromagnetism and ferroelectricity. And historically, a lot of these property arguments and symmetry constraints come from thermodynamic arguments where you draw your property relation and you take the second derivative and see if it's symmetric. And so again, for a lot of electronic devices, what we look for is you want control of your ordered parameter with your external knob, such as say electric field. And for devices, what we'd like to do is to kind of read out between states. So you read out between your remnant states. So for ferroelectricity, between your positive and negative remnant polarizations, and then the same thing for magnetism. Now, this chart is a little bit outdated, but one of the first undertakings we had for the project was to look for room temperature multiferroics or near room temperature multiferroics that we could integrate with the nitrides. Currently, to date, experimentally, there's not a lot of options still for good reasons. So one of the well-known ones, bismuth ferrite. We initially thought about integrating bismuth ferrite, but prior work done about 10 years ago from Daryl Shlom's group at Cornell showed that bismuth ferrite itself does not grow well directly on GaN. There's a need for intervening strontium titanate and titanium dioxide buffer layers, which still, the resulting film is epitaxial, but it results in a 180-degree twin variance when grown directly on GaN. So that in itself wasn't promising for epitaxial MBE growth. One of the things that Megan just explained in very nice detail was a possibility of the lutetium ferrite 113-124 superlattices. This was done at Cornell in the past, and this showed tunability in the ferroelectric Curie temperature as well as the Néel temperature for the magnetization. It was actually able to push the overall transition temperature near 281 Kelvin. So this was a material system. We thought, well, maybe this could work. And we know we're going to talk about the ferroelectricity of lutetium ferrite 113. And it's not really trivial how you can really obtain a polar distortion in your unit cell. There are many mechanisms that cause this, and the mechanism is going to dictate the actual strength of the interaction and what your actual spontaneous polarization parameter is. So something like bismuth ferrite, where it's very large value, close to 90, 100 microcoulombs per centimeter squared, that comes from the lone pair mechanism, essentially the bismuth 6s electrons. But lutetium ferrite being the geometric structure that actually pushes the spontaneous polarization down, in this case around 5 microcoulombs per centimeter squared. And that value, while still larger than kind of the electron concentration you'll see in a transistor, is still much closer, is closer to the ranges that we're targeting for electronic devices. And so as Megan mentioned before, one of the things we want to look for is this geometric rumpling, which is a signature of the improper ferroelectricity in the 113 phase that causes these very large lutetium atoms to rumple out of plane, which, as Megan showed, you can see in STEM. But one of the very, I think, important things for future electronic device application was that this improper ferroelectricity was predicted by theory. Craig Fenny's group at Cornell was predicted that this ferroelectricity was predicted to persist even down to essentially two unit cells or a monolayer and be less sensitive to the depolarization field out of plane or along the growth direction. And that's because the free energy landscape, the way you can write the Hamiltonian, is different for an improper ferroelectric versus a proper ferroelectric. So that's one of the things that we find very interesting. As well, brief overview about lutetium ferrite. We were talking about it itself is a low temperature multiferroic, magnetic ordering below 147 Kelvin. It has approximately electronically about a 1 EV band gap where the band edges are some iron 3D, oxygen 2p hybridization, and also iron 3D. You have magnetization in the plane. It's an A2 spin texture. And then asymmetric exchange, the DMI interaction also causes a canted out of plane weak ferromagnetic moment. And I think the really interesting about this that came up in the paper in 2014 was that this was predicted that this weak out-of-plane magnetization could be switched in the positive and negative z directions with an applied magnetic field, and that you could do that deterministically. So this aspect we thought was also extremely important for potential magnetoelectric devices. And so all these great things about lutetium ferrite. So what can the Nitride electronics platform provide for the oxides? Well, we know the nitrides have extremely great optoelectronic properties. You have band gaps that span from the infrared into the ultraviolet. You already have some existing piezoelectric and spontaneous polarization from the broken inversion symmetry. You can have polarization engineering in epitaxial structures where you can control the polarization from the growth direction and the band alignments, and that has led to novel electronic devices such as RTDs in recent years. So we think there's a lot of great directions we could do if we can actually epitaxially integrate oxides with nitrides. Now, briefly, so now we're going to look at trying to put lutetium ferrite, the 113 structure on GaN. So this was the first attempts that we were going to try. We were just on a primitive basic GaN on sapphire template, commercially available substrate. So it has approximately 6.5% lattice mismatch with GaN, so we weren't sure if it was going to work at first. From traditional epitaxy techniques, you would look at the in-plane lattice constant, you would see, well, maybe this is not great. One of the appealing things is lutetium ferrite is much more closely lattice matched to some topological insulators and also some epitaxial insulating magnets, which we can utilize in the future. So one of the first things we tried was try to grow lutetium ferrite on GaN. What happens? Is there a general growth window that you can use this for? So the great news is that it grows very well on GaN. It has a general growth window. And on our system, it's about the optimal conditions are 800 Celsius measured by a thermocouple. You see nice Pendelson fringes. And then you look along the 110 azimuth in the in situ read. This is a reflection high energy electron diffraction pattern. You can see that it is epitaxial with the underlying GaN and that it is single crystal. So this was the first report of essentially single crystal epitaxial lutetium ferrite on GaN. So once we determined that we could actually grow it and that there's a general growth window, we tried to look at, okay, well, is there any signature of ferroelectricity in these films? So what we did here was you take a semi-insulating silicon carbide substrate, grow a bottom electrode and GaN, 1 × 10 to the 19 per centimeter cube silicon doping, and then your PFN tip is obviously your top electrode. So we could see some hallmarks of traditional ferroelectric behavior, hysteresis, and essentially your strain behavior, and then you can actually see roughly 180 degree phase contrast during the loops. So this is essentially your PE loop. And from this, we're able to pole the surface in opposite polarities, extract an approximate coercive field. And this polling pattern is seen even after if you pole it, reduce the bias, scan, leave for an hour, do nothing, come back. you could still see these. You can still see this this box pattern. So we believe that this is not just purely charge injection on the surface. And then once we saw that, okay, this film, it grows on GaN and this ferroelectric, can we move this toward what we can do with electronic devices? So what we've been working on is you can buy this stack commercially, the MOCVD layer, and this is your two-dimensional electron gas, which is formed from a band offset of GaN and AlGaN layers. And you can see there's an electron accumulation that's going to happen here. So your channel is about 22 nanometers away from the surface, and it's generally high mobility, so you'll have about 1,000 centimeters squared per volt second or higher at room temperature. And the one thing here we were hopeful for is that leakage mechanisms in ferroelectrics are known, and so you essentially have 22 nanometers of an insulating barrier between your channel and carrier concentration that you want to modulate in the actual surface of your ferroelectric. So that's something that we thought might be beneficial. Our first growth we ever did generally suggested that the two-dimensional electron gas was preserved. If you just do van der Pol-Hall after the growth, you can see the traditional signatures of a 2-deg, which is essentially a constant or increasing mobility, an increasing mobility as you lower the temperature, and a constant carrier concentration. So I don't want to give away all my tricks here, but the oxide compounds, they have stoichiometry deviations that they can tolerate. So many oxides do. Lutetium ferrite is no different. So it can tolerate deviations in the form of excess or deficient iron or lutetium. So you have to be careful when it comes to matching your fluxes and tailoring your deposition conditions. And it's one of the cases where your actual in situ read doesn't really track well with what's happening with the surface in the XRD. But as we better tune the fluxes, the crystalline quality improves and our roughness goes down dramatically. Okay. And this is actually relatively showing a little more. This is actually, it's a straightforward case of as you increase your fluxes, your XRD peak intensity increases. You have a large scattering factor from the large lutetium atoms, so even like 20 nanometer films will give you large peaks for good crystalline films, and the rocking curve full with half maxes will decrease. So now I've shown too much. Now you know everything. And as you can see here, so once you optimize the growth conditions and protect the GaN surface, the lutetium ferrite crystalline peaks are extremely prominent. This full with half max of 1,020 arc seconds is the lowest reported, at least I've seen to date, of any film, because it grows very well on GaN. But even before, YSC is not the perfect substrate for lutetium ferrite. There's still a large lattice mismatch, as there is for GaN, but we're happy with the crystal quality as it stands. So one of the things we did on an unprocessed sample, what you can do is you can do a quick mercury probe CV. Essentially, your small mercury contact is your Schottky barrier, and the very large one is essentially your ohmic contact on the surface. So you could see the sharp modulation and capacitance over a narrow voltage range. That's indication of the 2-deg. You can integrate that area to get the charge, and then after we deposit the lutetium ferrite, we see a threshold voltage shift, and you can see the nature of the 2-deg is still likely there. So these are generally promising signs. And in collaboration with Lena Korkudis' group, we were able to look at high annular dark field STEM images. You could see that the actual GaN layer, this is a 2 nanometer GaN cap from the substrate. So this layer is actually preserved and it's not oxidized through during the ozone growth at all, which is great. And if we zoom in, we can actually see these characteristic rumblings that Megan showed earlier, and we could see even down to maybe the second layer, we could see these characteristic rumblings, which indicate maybe we can make really thin ferroelectric films in the future. So once we had enough structural confirmation that this was likely ferroelectric, we tried to process a FET out of it to actually work towards a ferroelectric field of FET. So essentially, you grow your layers, you pattern, you etch, you deposit your source drain contacts, you rapid thermal anneal, and then you mesa isolate, and then you deposit your gate by electron beam evaporation. And so we have not shown any direct ferroelectric behavior yet from the FET, but at the very least what we've shown is that certainly the 2deg is preserved, your channel is there, you have very large 8 orders of magnitude on-off ratio with actually a low gate leakage current, 10 to the negative 8 amps per millimeter. And then also on the same mask set, we have Hall bars. So you can take a Hall bar, load the sample in the PPMS, go down to 10 Kelvin. We tried to actually see was there any direct magnetoelectric coupling between lutetium iron oxide that could modulate the channel carrier concentration in the 2deg. So you could see, excuse me, Shubnikov to Haas oscillations around 7 Tesla. So this is really a direct result of you having a high mobility 2deg in the sample. There's really no asymmetry in the slope or the actual resistance plateau values, which would indicate that that's being modulated. So one of the things we hope to do in the future is to actually put an epitaxial magnet on top of this and see if we can further look at magnetotransport data. So in summary, this is the first report of epitaxial single crystalline lutetium iron oxide on GaN, a very high crystal quality. We have some suggestions that the film is ferroelectric, and we've made at least a FET, and now we're trying to see what we can do to actually make a ferroelectric FET out of these materials. So with that, I'll take any questions. Thank you.
Your curve last properties show that your lithium iron oxide works as just a dielectric. Is that your aim?
No, so we're hoping to actually use it as a ferroelectric, but right now, at room temperature, it seems to just act as a dielectric. Professor Ramesh at Berkeley actually showed nice hysteresis loops for LFO on platinum, I think, and iridium electrodes at lower temperatures. So we're hoping to go down to lower temperatures and repeat the measurements.
Okay.
Have you tried any growth on lattice matched InGaN?
Lattice match in
You said it
GaN.
was 6% too small.
No, we have not. That's a good idea. That would just involve more time. The only tricky thing with InGaN is that you can't go as high temperatures as you would like to, as you can with GaN, because indium nitride will start actually decomposing, or you'll selectively sublimate off indium. And at the growth temperatures we're using for LFO, that might be complicated, but it's worth a try.
When you say you want to make a ferroelectric FET, are you thinking about using something like negative capacitance? That's the goal, or?
Well, yeah, I mean, I guess negative capacitance would be you'd put an additional dielectric layer on top of the LFO, but in this case, we're hoping that you can obtain just an FE FET, and then you'd see a hysteresis in your drain current versus your VGS, and then the ultimate goal on top of that would actually be to have a magnet on top of this, and then gate control channel concentration via the magnetoelectric effect.
Okay, so not in principle, right? Okay.
So, I mean, the lutetium ferrite is completely relaxed. Is that
Yes.
true?
Yes.
So, do you see any issues with threading dislocations?
Yeah, that's a good question. We haven't. This is kind of a small one. We haven't seen them in STEM. I'm sure they're there, or if there's a way how if they're terminating here. I know the MOCVD substrates, I think their techniques generally are the dislocations terminate, I think by the end of the algan layer before the cap, but it's a good question that we haven't we don't have any insight into now currently, if those are affecting the switching behavior.
So if there are no other questions, let's thank Joe and all the speakers in the session.